Okay, it's my great honor to introduce Dr. Takashi Matsuwaki from the University of Tokyo. He will give us a very wonderful talk today. Dr. Takashi graduated from University of Tokyo and received his DVM degree and both DVM degree and PhD degree. And he also went to the Sweden for his postdoc fellowship. And today he is going to give us a talk. The title is Neuronal Mechanism of Information-Induced Change in the Body Temperature. Okay, let's welcome Dr. Matsuwaki.
Thank you very much for your great introduction. I think we have enough space, distance, so I can take out my mask now. Hello. Okay, today I will talk about this. I just found this topic is very hot for now. Today I will talk about this information-induced challenge in body temperature, how the body temperature is regulated under infectious conditions. First, please introduce myself briefly. I was born in Kagoshima. Kagoshima is southeast part of Japan Island. It's very near to Taiwan. So every time I come to Taiwan, I pass my hometown. And then as he introduced, I graduated from Tokyo University, and then I went to study in Sweden. It was very different from my hometown or different from Taiwan. It's very cold country. I will actually today's talk is many part of today's talk is collaboration with Sweden group, and then I'm now working in University of Tokyo as assistant professor. I'm a neuroendocrinologist and I'm neuroscientist, so it's I have some kind of topics working on now, and today I will talk this second line. Today's topic is, first I will talk about some general mechanism of cytokine to induce stress responses. And then I go deeper into my research. Infection, it's very hot topic now. Infection, when you have infection, you have a fever, or your hormone responses is induced, or you don't want to eat the food. It's all of them are controlled by your brain, central nervous system. Yeah, I have to show you. I have no fever, so no infection now. Don't worry. It's just in this morning I measured. And when we have infection, it's infection. The toxic infection comes to the peripheral tissue first, and then from peripheral tissue, the signal is transferred to the central nervous system, and then this central nervous system induces fever or disrupt your hormone patterns or suppress your appetites. In many cases, inflammatory cytokines works for these responses. Inflammatory cytokines are mediators of immune challenge, or they are secreted from many immune cells, and they are involved many different kinds of acute or chronic diseases, especially IL-1, IL-6, and tumor necrosis factor is very important. Today I will pick up this first one, interleukin-1, for this talk. Interleukin-1 is two different types of receptors. One is interleukin-1 receptor type 1, and then the other is type 2. Both of them are membrane protein. and their ligand is IL-1 alpha and IL-1 beta. They are expressed broadly in your body and also broadly in your brain, central nervous system. Actually, these two are different. Interleukin-1 receptor 1 is functional one. The 2 is decoy. They don't have any function. They don't have function. So in this study, I use interleukin-1 receptor 1 knockout mouse, which means if you use this knockout mice, you can see they can produce interleukin-1, but this interleukin-1 doesn't work in their body. It means you can use this mice to study about the function of interleukin-1 in the body. It's a experimental method, procedure. I use lipopolysaccharide for this experiment. Lipopolysaccharide is a membrane component of gram-negative bacteria. You can induce immune-challenged symptoms when you inject it to the animals or rats and mice. It means you can induce the fever, or you can suppress food intake, or you can induce hormone behavior, hormone disturbance in these mice. In this first experiment, I compared these responses between wild-type mice and interleukin-1 receptor 1 knockout mice. And then I measured hormone or food intake or body temperature. First, let me explain about the hormone stress responses in hormone. The neuroendocrinological stress responses is controlled by HPA axis. H means hypothalamus. P means pituitary. A is adrenal glands. When you were exposed, when the animals are exposed to some stressors, this stressor when this stressor's information comes to your brain, your body, or into your brain, the CRH, corticosterone releasing hormone, is increased, and this CRH comes to pituitary, and then from pituitary, ACTH is increased by this CRH, and this ACTH stimulates your adrenal gland, and finally, the glucocorticoids comes massively into your vessel, into your blood, peripheral blood, and these glucocorticoids work as an anti-stress regent. So in rats and mice, the most of glucocorticoids are corticosterone. Corticosterone is a major factor who is working as glucocorticoids. Oh, sorry. How can I back to? No. Ah. This one? Yeah, good. Yep. First, I compared this corticosterone level after injection of LPS between knockout mouse and wild-type mouse. As you can see, when you inject the LPS, 3 hours after injection, both wild-type and knockout mice has increase of this corticosterone level. It means both wild-type and knockout respond the LPS injection. They have, and it means knockout mouse has normal responsibility to the LPS as wild-type have. This is the immunostaining experiment on the hypothalamus. This black dot is the cells, immune positive cells for the C-force. C-force is marker for the activated neuron. It means, so this black dot means activated neuron. When you inject LPS to the mice, this black dot increase. It means activated neurons are increased. So if you see if you compare these two, wild type and knockout has similar level of activation of the neurons. It means wild type has normal responsibility to the LPS injection. This is, I compared the food intake between wild type and knockout. Again, knockout and wild type has similar level to the similar responses to the LPS. It means the gray part is dark phase. The rodents, rats and mice, have eat food in the dark phase. So when you usually this is control. Usually they eat a lot in the dark phase, and then after light turn on, the food intake decrease, something like that. And then when you inject LPS, their food intake decrease like this, the suppressed. Then both wild type knockout has similar level of decreasing. It means IL-1 receptor 1 deficiency does not affect LPS induced anorexia. So for now I checked hormone level and anorexia food intake level, and there are no difference between wild type and knockout. So how about fever? For measuring body temperature, I use this system. This is transponder, the telemeter. Oh, thank you. This is telemeter I implanted into the mice body. Okay. This is telemeter I implanted into the mice body, and you can see it's very small. Oh, sorry, it's Japanese coin, so you don't know how small it is. It's very small. This is very small. And then if you implant this telemeter into the mouse body, you can trace the body temperature. The black is dark phase, white is light phase. And I implanted it here. So first the temperature is very shaggy. And then maybe after 1 week they have some balance, and then after 2 or 3 weeks later you can see the very vivid change of the body temperature between light phase and dark phase, as you can see here. So using this system, I measure the body temperature after LPS injection, and then compare it between the wild type animals and knockout animal. As you can see, the blue line is wild type, and in wild type, when you inject LPS here, after maybe 3 hours or 5, the body temperature is increasing. They have fever, and then after 5 hours, they have peak here like this. And this peak is, interestingly, this peak is suppressed in the knockout mice. It means IL-1 works for this fever. So it means this cytokine in IL-1 from the peripheral blood come to the brain, and then it works for this fever. But how? So next I checked how this IL-1 works for the inducing fever. And first I focused this prostaglandin E2, because prostaglandin E2 is famous as a strong pyrogen, it makes fever. It's very famous. So I just compare these two. Compares these two the prostaglandin E2 level in CSF. CSF is the cerebrospinal fluid, the fluid in the brain. And then, as you can see, the level of prostaglandin E2 is much lower in knockout mice. So it means this prostaglandin E2 is one of the causes of this difference of the fever in between wild type and knockout. But we still have problem. Between peripheral blood and the brain, there is a strong barrier. It means it's called blood-brain barrier. We call this blood-brain barrier. Because of this blood-brain barrier, your brain or our brain is separated from the peripheral blood. But how can these cytokines come over this blood-brain barrier, BBB, and then make or induce fever? Actually, there are some stories already. One is that there are some people believe that in some part of the brain we have some space in the blood-brain barrier, so the cytokine can go can go through this blood-brain barrier like this. And the other story is in the afferent vagal pathway. They have a receptor of cytokine. Then the cytokine who bind to this receptor can go. The signal can go through this into the brain. But so I first check these two stories hypothesis with tissue-specific knockout mice. This is cell-specific. The neuron-specific knockout mice. It's the mice lacking the IL-1 receptor 1 only in neurons. It means I inject LPS to these knockout mice, and then there are no difference between the wild type and this neuron-specific knockout mice. It means the IL-1 receptor 1 in neuron doesn't work anything for this in LPS induced fever. And then I also checked the second story with this afferent specific IL-1 receptor knockout mice. And then also there are no difference between wild type and this cell-specific knockout mice. It means this IL-1 receptor 1 in afferent they have no effect in this fever. Finally, I checked with this. It's endothelial cell-specific knockout mice. In endothelial specific knockout mice, there are significant difference as we saw in the whole body knockout mice. You can see here, comparing with wild type mice, this endothelial cell specific knockout mice has a suppressed fever. It means the IL-1 receptor 1 in endothelial cell works for this LPS inducible fever. And then I checked more for these endothelial cells. Endothelial cells is on the vessels in brain, and this the prostaglandin E2, the strong pyrogen. We have checked in this paper. They reported that brain vessel produces prostaglandin E2 responding to the cytokine IL-1 beta. So I checked this mice. This mice is endothelial cell specific MPGS1 knockout mice. MPGS1 is the enzyme, synthesizing enzyme of PGE2. It means this mice doesn't produce PGE2. This mice doesn't PGE2 in endothelial cell. So in this mice, when we injected LPS here, the fever in like wild type doesn't come out in this mice. It means endothelial cell, MPGS1 in endothelial cell works for this fever. So for here we have the hypothesis. When we have when we have infection in peripheral tissue, or peripheral blood, this cytokine or IL-1 binds to the receptor in endothelial cell, and then from this endothelial cell, prostaglandin E2 is produced, and this prostaglandin E2 go through this brain, and then it works in brain to produce fever. This is one hypothesis we have produced. Are you waking? I'm watching. And next I go deeper in this regulation, thermoregulation system. Many years ago, my former group published one paper with this MPGS1 knockout mice. This MPGS1 knockout mice is whole body knockout. This knockout mice, they say this knockout mice doesn't produce any fever when they injected LPS to the mice. But some years ago, when I was checking this, when I was doing similar experiment, I found that some of them produce not fever, but very low temperature, the hypothermia, very much. Their temperature decreased a lot. But not all of them wild knockout mice produce hypothermia. Some mice have this hypothermia. I was wondering why. And first we try to classify them depending on their sex. See, you can see in wild type, of course, they have no hypothermia. They have fever. Almost all of them have hypothermia. On the other hand, knockout mice, almost all of them who has hypothermia was female. Unfortunately, I don't know why, but only one male has hypothermia. But most of them are female. But not all the female has hypothermia after LPS injection. Why? What is female have, but male don't have? How do you think? I'm physiologist, so first we focused on the estrous cycle in the mice, and then we checked their estrous cycle. In rodents, they have 4 or 5 days estrous cycle because they don't have luteal phase. They have very short estrous cycle. The estrus, proestrus, and estrus. So first we classify them depending on their estrus stages, like this. Can you guess which is which? Do you have any idea? Most of the animals who had the hypothermia was proestrus animals. Why? Like something like that. I think only one de-estrus mice has hypothermia, but most of them are proestrus mice, something like that. So here I came to one hypothesis. Usually when we got infection, prostaglandin E2 is increased in our body, and then this prostaglandin E2 works on our hyperthermic center. It is said this hyperthermic center is in hypothalamus. But from our result, there should be some hypothalamic center in the brain as well, because when they don't have this, they got very acute and very high, deep drop of their body temperature. It means they should have some hypothalamic center. This drive. Then this drive is affected by something from ovary. This is our hypothesis. And then we go forward more. What is coming from ovary to affect this hypothalamic center? And we focus estrogen because in proestrus stage, the estrogen concentration is very high, as you know. So we focused on estrogen. First, we ovarectomized. We removed the ovary from this female mice, from knockout mice. And then, interestingly, this ratio of LPS-induced hypothermia was very decreased. Again, only one female still have the hypothermia induced by LPS. We don't know why, but it happens, this kind of experiment, as you know. And then when we treat them with estrogen, this high ratio is recovered. It means estrogen has some effect on this LPS-induced hypothermia in the MPGS1 knockout rats. MPGS1 knockout mice. This is the temperature data. When you inject LPS, this one is OVX, ovary rectomized mice. When you ovary rectomize, even after LPS injection, the body temperature doesn't change. They don't get fever or they don't get the hypothermia. But if you treat them with estrogen before LPS injection, this hypothermia comes again. So summary 2 is, as well as hyperthalamic center, there should be a hypothalamic center in the brain whose sensitivity is affected by estrogen. And then the second is both hyper and hypothalamic centers are activated by infectious stimuli. This is my laboratory group, and this is my former laboratory group. Most of the experiments are done in these two groups. Thank you very much. And unfortunately, this time I can't talk in front of most of the students. So if you have any question, you can send me the question in this to this mail address. I'm talking to you. Thank you very much. Mhm.
And I want to ask, if we just take out the ovary of the mice,
Mhm.
will the mice temperature after we inject the LPS into the mice, will the mice temperature be even more higher than before? If we just take the ovary out.
You mean in wild type?
Yeah, wild type.
Usually, it is said the female has lower temperature in wild, comparing with male. And then I didn't compare them. It should be. Mhm.
And the wild type
Mhm.
will the female mice become, the temperature become even higher than before?
I haven't checked, but it should be changed a bit, because basically estrogen is said it's said to control some temperature, and they have some effect to enhance the temperature. Yeah.
Sorry, I wanted to ask, as in female models of hyperthermia, there are often cases observed that have cognitive impairment and disruptive behavior. So I wanted to ask if during this experiment and when hypothermia was present, did we observe any of these sorts of disruptive behaviors?
Oh, you mean?
Oh, sorry. So in human
Is it
models,
okay?
yeah, I was doing some research as you were speaking, and so I see that in human models, often that hypothermia is paired with cognitive impairment and disruptive behavior. So it's yeah. And I wanted to ask if during this experiment we observed any sort of disruptive behavior in the mice.
Which kind of behavior? Look, we just could record the locomotor activity, and then there are not so many difference. But as you know, the estrogen increased the locomotor activity in rodents. So I think if you compare the basic level, there should be difference. When you treat them, the estrogen, their locomotor activity increased very much. Yeah, usually when you check the, how do I say, the intact rats or mice, and then you can see the difference between the estrous cycle. In the estrous cycle, in the progesterone cycle, they are very active, very much, and then their food intake decrease. Yeah, so there should be difference.
I have one question. Well, first of all, you mentioned that the IL-1 effect is through the post-aquatic E2. Is there any link mechanism to link these two substances? How the IL-1 to increase the post-aquatic?
IL-1 basically first the IL-1 increase in the peripheral blood, and then this IL-1 bind to the receptor on endothelial cell, and this endothelial cell produce prostaglandin E2. So the there is linked very much. Yeah.
I have some question about, for most of your study, you use knockout mouse. It's very impressive to have to create so many kind of model. But you knock out some receptor. I'm curious about the phenotype of this animal, or do you use other ways like pharmacological method to
Yeah.
do the
Yeah.
experiment, or maybe for example, if the hypothermia is caused by maybe they consuming less, or their activity is less lesser. It's not because of they have a hypothermia centrally, whereas it's other peripheral effect.
Yeah, the difficult thing for the prostaglandin E2 is they have 4 different receptors. So yeah, there are some chemicals, antagonists for these receptors, but it's very not specific and it's very difficult to, you have to think about this combination. So first we just decrease all of them. And as for the IL-1, we have already done with the antagonist, and then the result was similar, very similar. I mean, when you treat the antagonist for IL-1 receptor, the body temperature was decreased. Yeah, we also combine this chemical experiment as genetic experiment as well.
There's no more question. We have some souvenir for Matsuwaki, director from the Neurobiology and Cognitive Center at the lab.
Yeah. It's our pleasure to have Dr. Matsuwaki to come all the way from Japan to Taiwan. I'm sorry that this is our first time to try the online seminar. So I hope all of the students and you can enjoy this seminar, and also hopefully next time when you come to Taiwan, you can enjoy Taiwan more.
Okay. Yeah.
So on behalf of the Neurobiology and Cognitive Science Center, here is the small souvenir for you.
Thank you very much.
Yeah, so you can take a look and hope you enjoy it.
Wow.
Yeah,
Thank you.